Hi, welcome back to Book Club. So today we're still in applied numerical methods. Again, that's going to be Python. And this is actually a really important day. This is where we convert, physics, chemistry, biology, whatever we have, is where we convert it to something on a computer. This is the discretization process. And what I'm talking about here is integration and differentiation. Right, so this is integration and differentiation. Now, because everything that we study in the real world is usually not algebra, unless you're just doing geometry and what's the area of a circle or that kind of stuff. Most of this is integration and differentiation. So if I have some curve, we have usually two questions on this curve. From, say here, A to B. One might be, what is the slope at any given point of this curve? So we might want to know what's the slope. Or we might want to know what the area is, the full sum. And the way we do that on a computer is the process of discretization. So we're going to focus on integration first, and then we'll come back to differentiation. So integration is actually, what we'll do is we'll take each little bit of this and add up. And so here's this little sliver, we'll call it dx, assume this is the x-axis and this is some function with respect to x. And what we're trying to do is integrate f of x as a function of x. Okay, so what we do though is we are going to turn this into a sum. To be explicit here, I'll say it's a sum over n things, and we want to add this up. Now, a very simple way would just be to take f at x I, so for I is equal to 1 to n, and multiply by dx. That's a very simple way. Okay. And what you can think about is that's basically one side. It's either the left side of this rectangle or the right side of the rectangle. That's first order accurate. We'll talk a little bit about what that means a little bit later. But the more accurate version is actually to think imagine each point of these curves as adding up a whole bunch of trapezoids. Okay, where you have sort of the height of one plus the height of the other. So if you've ever, going back to your elementary days, if you've done the sort of the area of a trapezoid. Okay, what you would look at here, let's call this A, and then B, and then C, and then this, let's call each one of these the x's, just to be very simple. And so you would actually say the area of this trapezoid is dx, and you would take A plus B, kind of average them over 2. And then if you added up the next one, you would then add dx, and then it would be B plus C over 2. Okay? So if you do that math, you see how the b's add together. Then this is actually a pretty easy thing where you basically say f of x0 over 2 plus f of nth over 2, that's times dx. And then you just sum I is equal to 1 to n minus 1 f of x dx. Okay? We do the trapezoidal. And this is second order accurate, okay? And we'll talk about that here in a little bit. But the error based on this integral, this is order dx squared, okay? And so what we're talking about, so we can actually do this for a function that we know analytically, right? We have all these math functions. We know exactly how to integrate, so we could run all of these algorithms. And there's a whole host of them. These are the most common ones. And what we'll find is that there's an error. In fact, this is going to be the log of the error versus, and actually I'm going to use n here, capital N, so that way, higher resolution to the right. And what always ends up happening is you have some amount of error that's big, and then you finally resolve the physics, or you finally have enough resolution on these slices to resolve sort of the interesting curves, if you will, and then the error goes down at some rate. And so when we know the trapezoidal is second order, actually on this log scale, this is log n as well, this would go down at a -2 rate. Okay? But there's a whole host of these algorithms. In fact, if we come back to this thing here, where we have f of x, really in general, I'm going to write this down here, and I'll write it in green, just to highlight. In general, what we're actually doing, this is called quadrature. Quadrature. And we're actually saying the integral okay, which is integral of f of x dx, is actually some sum of f evaluated at a point x of I times some ith weight, okay? And we don't necessarily imply that I is evenly spaced. And so in fact, there's a whole host of formulas where you actually, that are, derive, the derivation I'm not going to do here, a little bit more complicated, effectively where you say, hey, I'm going to let both the x and the weights float, and you can achieve, in fact, some incredible accuracies. And this is some of the methods I did as a professor in numerical simulation of turbulence, but we would use spectral methods, okay? And so what happens here is, there's a second order method, I could draw a fourth order method, but what happens in spectral is you actually get this exponential roll-off. So this is spectral. So if you ever heard of, so Legendre polynomials are one set, Chebyshev polynomials are another set. So there's some really advanced stuff here. And in fact, what's interesting is if you have a function that's periodic, actually, the best one is it's even spaced, and it is spectral. Okay, it's basically because it's the Fourier series. Now, we'll talk about that here in a second as we get into differentiation. So the other half of this one, which is I have a function, and I'm trying to understand f prime of x, right? Or the derivative of f with respect to x. Okay, so for this one, the easiest way to go through some of these basic derivations, and again there are lots, is the Taylor series. And so let's imagine we have we know the function at f. In fact, we know all the functions. If you're doing differentiation, we know the function. And so what we do is we estimate what is the function x plus, and I'll keep it consistent here, dx. So a little bit away from f. That's the f of x. This is the Taylor series. And then it's dx times f prime of x. And then it's dx squared over 2 f double prime of x. Okay. In fact, I'm running out of room here on the screen. But basically, it's this Taylor series that would kind of continue on. Let's see if I can squeeze in one more. And it's getting tight. I'll do it down here. Plus dx cubed over 6. So this is a factorial times f triple prime of x. Okay, so that's x plus dx. If we then repeat this, x minus dx, so going back a dx step, it's the same thing here, f of x, but now that dx is negative, so there's a minus f prime. I'll leave out the f of x to give myself more room, and then the dx is squared, so I get a plus dx squared over 2, the negatives cancel, and that's f double prime, and then a minus dx cubed over 6 f triple prime. Okay, so if we're interested for the first derivative, look what happens if I add these two. So if I add both of these, on the left I'll have f of x plus dx plus f of x minus dx. If I add them here, I'll have 2 f of x, and then anyways, I'll finish this out. If you add them, I'm going to get the second derivative. That's okay. We'll do that one first. The first derivatives cancel, and then you would have plus dx squared, right, f of f double prime. The triple derivatives cancel, and then we would have plus dx to the fourth f of 4x. All right. So I'll do the second derivative. Fine. I was going to do them both anyways. All right. So now that we've added them, we can solve for f double prime. So here's the second derivative of x, and push everything else to the other side. So you have f of x plus dx plus f of x minus dx minus 2 f of x over dx squared, and then you're left with a term that's order dx squared. All right, so that's the second derivative. And this is called finite difference. This whole process, finite difference. All right, now in green, I'm going to come back here and do what I meant to do first, which is subtract the two equations. Okay, so that gives you a second derivative. If I subtract these two equations, we will then have f of x plus dx minus f of x minus dx Okay, now let's see what cancels. So f of x cancels. We get twice dx f prime. The second derivative cancels, and then we have third derivative dx cubed over 3 f triple prime, and that's enough. Okay, so now let's solve for f prime. So similarly, we'll have f prime is equal to f of x plus dx minus f of x minus dx over dx, and then this is accurate again to dx squared. All right, so that's the first derivative. And so if you have a function and you want to know the first derivative, you could just follow this formula kind of as you're kind of stepping through. Basically, this looks to the right and looks to the left of the function and uses that information to figure it out. So graphically, right, you would come here and you would look at the point ahead of it and the point behind of it to figure out the slope. Or if you're trying to figure out the curvature, which is second derivative, you would use the point that you're at as well as the one to the right and the one to the left. That's what this formula is. Okay. So this is this finite difference. There are a couple more advanced ones we'll get to sort of maybe in a later chapter, later section. But this is the root of a whole bunch of algorithms. And so as we get into ordinary differential equations or partial differential equations, this is sort of the root of it. And many things, finite difference is this doesn't you don't have to keep evenly spaced. You can adjust all these things. And so really, there's sort of a powerful formula that's equivalent. And so I'll just finish by saying kind of one more thing to kind of, again, talk about the spectral. So again, when I'm integrating, I can have this formula where I'm allowing x, y, and wi to do it. Same sort of thing in the spectral method. I can actually cast my function as a series. The most famous one is Fourier. So again, if this is a Fourier series, remember f can be written, we did this last time, can be written as sort of a frequency, fn, times, and I'll write it e to the I n x. That combines both the sines and the cosines. Okay, so if you have that, then guess what? If you're looking for, say, what's the second derivative? Well, if you know how it expands, in this case, that's literally just n squared f of n e to the I n x, and there's a minus. Okay, the I and x comes twice. So there's an equivalent powerful way if you expand. This happens to be a Fourier series. If you expand it in sort of Chebyshev or Legendre, again, that's the kind of stuff I did as a professor. You can again get the spectral resolution if needed. So sometimes some analyses you're working on are actually very, very important to drive this error quickly away to zero. And one of the reasons for it, I've mentioned it a couple of times. If you're actually using this method to generate a matrix, to kind of turn your problem into ax equals f, where you're inverting this matrix, sometimes the difference between, if you're trying to resolve here on the computer, sometimes the difference between this and the second order method can be a factor of 10. And remember how to invert this, it goes like n squared? Well, if I have a factor of 10, then that's a factor of 100. It actually, sometimes, having the higher order method actually reduces your computational time because you're trying to get to, say, a couple digits of accuracy, or maybe it's 5 digits. You're still holding sort of 16 digits on the computer, but you want the error of your algorithm here to be low. So that's part of it. So anyways, in conclusion, there's some basic finite differences for derivatives. So this is sort of your basic stuff that you might see in a sort of entry-level computational math class. You have your basic integral, which is basically adding up slivers, or adding up trapezoids, which is a little bit more accurate. And then on both of these, there are spectrums where you can add the higher accuracy, including ways where you can get to the spectral accuracy by, in this case, in the quadrature, and by letting both the locations in the weight floats, or in the case of the derivative, by expanding sort of the function in its basis form, and then know the exact form of the derivative of the basis. So we'll see you next time.